HumanMAC, masked motion completion for human motion prediction. Human motion prediction is a classical problem in computer vision and computer graphics, which has a wide range of practical applications. The problem of human motion prediction, HMP, focuses on predicting possible future pose sequences from a sequence of observed motions. Prior state-of-the-art methods work in an encoding-decoding fashion to tackle the HMP problem. Technically, these methods first encode the previous motion frames to latent representations explicitly, and then decode the latent representations into prediction results. Although these methods enjoy the good performance in some scenarios, they are still unsatisfactory in practice. We detail the issues from three aspects. Firstly, most state-of-the-art methods rely on multiple loss constraints for high-quality prediction results. Consequently, they need carefully designed hyperparameters to balance different loss constraints, which makes it laborious for method applications. Secondly, previous state-of-the-art methods need multi-stage training. That is to say, the learning of the encoder, decoder, and sampling in the latent space is performed in different stages. Moreover, for the methods, it is hard to realize the switch of different categories of motions, like switch from walk dog to sitting, which is pivotal for result diversity. The reason is that these methods are largely limited to observed motion sequences for prediction, which include few such switches. In this paper, we get out of the encoding-decoding fashion and propose the masked motion completion framework named HumanMAC to handle the HMP problem. To the best of our knowledge, this is the first time to tackle HMP from the perspective of masked completion. Compared with the methods in the encoding-decoding fashion, HumanMAC enjoys the following great properties. Firstly, during training, there is only one loss function in the objective of HumanMAC. Secondly, HumanMAC is trained in an end-to-end manner, which is remarkably simpler to implement than multi-stage training. Furthermore, HumanMAC can achieve more diverse prediction results that contain the switch of different categories of motions, even though the switch is rare or not presented in observed motion sequences. Previous work proposed the discrete cosine transform, DCT, to predict and generate human motions. The DCT operation extracts both current and periodic temporal properties from the motion sequence, which is beneficial for obtaining continuous motions. Therefore, we train our model with DCT. In the training stage, we train our motion diffusion model in the DCT domain. We train our proposed noise prediction network translinear with the only noise prediction loss. In the inference stage, given observed motions, we need to use the trained model to make predicted motions. In prior diffusion-based works, with a trained diffusion model, motions can be generated via denoising steps. However, the prior procedure cannot make use of observed motions, which makes predicted motions uncontrollable. To address the issue, we propose a new completion algorithm without model retraining, named DCT completion, which can complete prediction motions with observation motions. In a trained diffusion model, the noisy observation spectrum and denoised prediction spectrum are approximately the same distribution. Therefore, we project the denoised and noisy spectrum to the temporal domain via the IDCT operation and then combine them together with a masking mechanism. For the motion switchability, we provide the final additional M-frame target motions in the inference stage to obtain the controllable prediction. We compare our method with DLO and GSPS. Although the DLO and GSPS methods seem more diverse, both of them generate some failure cases with large distances to ground truths, which are not reasonable motions. We claim that the diversity exhibited by artificial metrics and the comparison of multiple predicted results are unreasonable, resulting in a large number of failure cases. We highlight the failure cases of baselines that do not satisfy the physical constraints of the human center of gravity. In addition, taking walk dog as an example, the prediction motions of the baseline work are relatively slow and eventually tend to be static. However, our method can predict relatively high-speed motions. This result is mainly due to the fact that our modeling of observation and prediction motions is global, and the encoding-decoding methods are separate for the modeling of the observation and prediction. The proposed HumanMAC enables the switchability between different categories of motions by applying free training DCT completion. The ability helps produce some motion combinations that are rare or unseen during training. In the case where the directions of the human body facing to differ significantly, HumanMAC accomplishes the switch from one direction to the other smoothly and naturally. For transferring between two motions with a large distribution gap, like from sitting to standing, the motion of the upper and lower bodies changes in a natural way. Due to the flexibility of the mask mechanism in the DCT completion algorithm, we can complete the F-frame unknown part-body motion by providing the H-frame observation and final F-frame specified part-body motions. The baselines GSPS and DLO only can achieve upper-lower body control since they need to disentangle the upper and lower body motions. Besides, with disentangled motions, these methods need to retrain the model to achieve the part-body controllable ability. However, our method does not rely on model retraining and can achieve controllable prediction of any part of the body. We present the generalization ability of the HumanMAC via zero-shot adaptation experiments. Here we train the HumanMAC model on the human 3.6M dataset and predict motions via the given AMAS dataset observed motions. Our zero-shot motion prediction results on AMAS dataset are reasonable and diverse, which shows the good generalization ability of the HumanMAC framework. Thank you for watching.